Excellent. Thank you, Patrick. Good to see all of you. I hope you all are doing well. Yesterday, Claire and I got to meet with one of the students working on, one of you guys working on the next design challenge, and I really enjoy that. And it also gives us some really valuable feedback. I was reflecting, like, have you put it together how new this stuff is that we're doing in this course? Like, I have never taught anyone using Onshape before. So this is my first go at it. And we are very interested in getting feedback as we go about what are the things that are confusing and what are the things that are easy to pick up on. And that is yet another reason why I want you to start on challenges before the last minute, because there is almost certainly some pieces of the design challenges that are going to trip you up. And so if you start on them early and give yourself time to ask questions and not be in panic mode, all will be good. If you try to do it the last night, I'm pretty sure it's going to be a very stressful and uneducational experience for you. So start on those. And we updated the syllabus. And Patrick, I didn't mention this to you, but I put it on the syllabus whenever there's a draft that's due on Tuesday, so that we make sure that you're like halfway done with the assignment 2 days before it's due, to help reduce the possibility that you wait until Thursday to start on it. And I've been having a lot of fun because I am realizing, oh man, I'm right now working on design of the front end of the plant, the chemical feed system. And I'm like, oh, well, I can put some of the images from that into the presentation. And these are images that have never before been seen because some of them were created this morning. So that's fun for me too. We're gonna talk about flow control today eventually, but Claire pointed out to me that I'm giving you all an assignment dealing with the entrance tank, which is where the flow control and the flow measurement system is happening. And I haven't talked at all about entrance tank. And guess what? There's a chapter in the textbook, brand new, written by one of my former students, Emily Wood, on the entrance tank and its design. And so that is there for you to look at. And I'll introduce the entrance tank just briefly today before we then go down the more specific path of how do you measure and control flow in a water treatment plant, or indeed anywhere. So to get started, flow control and measurement, it's creativity without a trip. It's variations on a drip. It's giving head loss to slip, and it's chemical doses that don't dip. So that's what we'll be talking about. And entrance tank got added to this long list of things that we're going to talk about over the next 2 sessions. So entrance tank. So this entrance tank is what I was talking about, hot off the press. I just added the chemical dosing, the doser system to this morning. Let's look inside, and we're not going to worry about the chemical dosing system until much later, like almost at the end of the next session. Inside are all these pieces, and water enters through this pipe. And I should have made an animation here, but I got distracted. So water flows down into the entrance tank. I'm assuming you can follow my cursor. It's going to get deflected by this sloped bottom and end up heading over in this direction. And it's basically going to make a big eddy here and circle back and then go through. Here's some trash racks. Here's where the dose controller is for the chemical feed. It's picking off the water level there to figure out what it's doing. This long section of the entrance tank is about providing an opportunity for pretty high density particles, grit, like think small sand, for it to settle out so that it doesn't end up like clogging our flocculator. So things that would have settled out anyway in the plant, you want to catch them here so they don't settle out and give you a maintenance issue later on in the plant. And the way that the grit is handled is it's going to drop into these hoppers, and if the hopper begins to fill up, the plant operator can grab a hold of this 2-inch diameter PVC pipe, pull it up. That unplugs it from the socket that's embedded in the concrete in the bottom of this hopper. The socket is like a coupling that would normally be used to connect two pieces of pipe together, but that coupling socket is embedded in the concrete. So when the operator pulls this pipe out, there's a hole in the bottom of the tank that the solids can slide through and go down into this bottom part, which is this big channel that ends up dumping into the main drain channel for the plant. The next piece is the water exiting the place where the sedimentation is happening goes to this linear flow orifice meter. This is a device that was specifically designed to get a linear relationship between flow rate and the depth of water in this tank, and we'll talk more about that later. So that's all happening inside this entrance tank. So for the entrance tank design, you're going to be thinking about, well, how big does the entrance tank have to be so that there's enough time for particles to be captured by them falling down? And to be fair, we're going to talk about sedimentation, I don't know, 4 weeks out or something, but it's not so complicated. You can just remember now that the trick for sedimentation is that the only thing that matters in a tank is the plan view area. So all that matters is the plan view area. That's what's going to determine how much sediment is able to be removed. And so it's looking down on this tank from above, what's the area that this plant provides for particles to settle out? It kind of makes sense, right? We're relying on gravity, and gravity's pulling things down to the bottom of the tank. And so it's that bottom surface area that matters. Here's the inside of where the trash rack is. And you might be thinking about, why do we need a trash rack? What's so important about that? Our trash rack is maybe even more important in our plant design than in conventional designs, because the very first place where water that goes through our flocculator and then is going into our sedimentation tanks, before there's really been any opportunity for more particle removal, the water is going into the sedimentation tank and it's having to flow through an exit that is about 3 millimeters wide. So there's a gap that the water has to flow through that's only 3 millimeters wide. And that means that our trash rack has to catch everything that's bigger than 3 millimeters. Otherwise, it's going to land in these diffusers that are in the bottom of our sedimentation tank. They're going to clog and it's going to be a maintenance issue. And here's actually an opportunity for some creativity. It turns out like this is one of these, like in one sense, it's a very simple device. It needs to provide a gap that's smaller than 3 millimeter and catch debris. Think leaves and twigs and fish and crayfish. It needs to catch all of that stuff before it would go further into the plant. And the various designs that have been built over the years have had problems. We weren't being detailed enough in our designs. We weren't providing a design that looked like this even. It was even less detailed than this. And so our partner in Honduras was trying various things to make a trash rack. And often the porosity, meaning the fraction of the open area, wasn't high enough in the systems that they made. And so the head loss was too high. And I'm wondering, given what we talked about lately, do you see the connection? If the trash rack doesn't have very much open area, then why does that make the head loss higher? And would you be able to tell me what the head loss through the trash rack, what it might scale with? And I think I'm going to ask you the question. Do you think the head loss through a trash rack is going to scale or be proportional to the velocity of water through the trash rack? Or is it going to scale with the velocity squared of the water through the trash rack? Ooh, think about that one just for like 15 seconds. Does head loss through the trash rack scale with velocity or with velocity squared? And I'll just ask for a show of hands. Okay, let's do it. Who says that the head loss or the pressure drop or the change in elevation across the trash rack, as you see here, right? I have those I have two like sheets that I'm trying to show the elevation of water upstream of the trash rack and downstream of the trash rack. Is that change in elevation going to scale with velocity? Who says it's going to scale with velocity? With v to the first power? Who says it's going to scale with v to the second power? Wow, you guys rock. You guys are amazing. That's great. You're exactly right. It does scale with v squared because it's a minor loss, or said even better, the loss is about the flow expansion that happens on the downstream side of the trash rack. So water contracts into these narrow spaces, it expands coming out the other side. And so that expansion is where the turbulence is generated and where the head loss happens. And that a head loss from an expansion goes with v squared. And by the way, I don't know if you picked up on this, but that's true even if the flow is laminar. It's like, oh my goodness, that's crazy. If you have a flow into, even if you have a pipe that's discharging water into a big lake, and even if the flow out of that pipe is laminar, all of the kinetic energy is lost when it flows into the lake, and that is v squared. So it always scales with v squared when you're doing an expansion. Okay, man, you guys make me happy. You got v squared as your friend now. So that the potential place for some creativity, and I haven't thought a whole lot about potential projects for this class, but we'll think about that as we get closer to that time. This might be a potential project. We need a good fabrication method for a trash rack that has a high porosity. And the way I'm showing a high porosity is, you can think of this as like guitar strings that are somehow kept tight. And that somehow kept tight is the part that I don't know how to do. So that could be a potential project to figure out, how would you fabricate a simple system that allows you to have wires kept tight that would maintain that 3 millimeter gap. It would be easy to clean. Okay, I'm good with that. Here's another section view of the entrance tank showing what's happening inside. And I'm curious, do any of you have any questions? Like you got the idea, water is coming in out of this pipe. It ends up being chaotic at this front end. I'm not exactly sure what all is happening, but because of the way I've designed this, water's probably going around and then flowing back across in this direction, going through the trash rack, 1 or 2 trash racks, and then past all these hoppers where grit can be settling out, and then into the pipe where it gets into that pipe by going through little holes in the side of the pipe, and then goes down to the bottom of that pipe and exits and goes into the flocculator. And Michael's got a question.
I do, Monroe. First of all, very timely, because in your presentation last week, the students in Capstone, we saw this new entrance tank, which we had never seen before. But yeah. I'm curious if you could explain a little bit why. I understand the idea of the hopper, but was there anything to the geometry of the hopper, the height of it, the slope of it, that would be of interest to me?
That's excellent, excellent. Man, I would say, were you looking at my notes beforehand, or what happened? So I'm not going to answer your question. I'm going to just keep right on going. This is about design thinking. And Michael asked a perfect question, like, well, where did that height come from? And that's actually a really good question, because if I tell him I looked it up in a book, that's not very helpful to Michael. It doesn't really help explain, like, well, where did that come from? And if I say, oh, it doesn't matter, then Michael knows that I don't understand physics, because it always matters. And that's like a key insight. When you're designing something, there are no random dimensions. There aren't any dimensions that it's just like, oh, you can pick anything you want here. There's always something that constrains it. So no dimensions are arbitrary. There are always constraints. And this is true whether it's an evolutionary trait like the diameter of your femur, or an engineered device like the diameter of a bicycle wheel. In all cases, there's something, and you shouldn't have to think too hard to figure out like what might be constraining each of those. So what's constraining it? Often it's physics, or for that matter, biology or chemistry. I had a physics minor, and so I tend to think of the world as it's all about physics. I know that the microbiologists would disagree with me, but anyway, so I say it's about physics. And there's Michael's question, like, well, what about that slope in the hopper? Where did that come from? Well, what would you like? What would you like to have happen in this hopper? You would like it if, when you pull the plug out of that hopper, you would like it if the hopper would drain, meaning all the sediment that's sitting there would slide down and go out the hole. And this is very similar to, I don't know if you have, are there any places in Ohio where there are cliffs, or where there is hillsides, where there is, I think it's called scree, where there's like rubble coming off the side of a mountain, and the slope that you get it's the angle of repose. It's the slope that you get that's just barely stable. And usually where there's scree, and if it's close to a hiking spot, there'll be signs there. Don't hike on this, because the whole thing is just waiting for an avalanche, right? You don't hike on scree. Well, we're trying to create a system where all there is it's avalanche ready. It's steep enough so things will slide down. So if I look at that, it looks like my angle is probably 50 degrees, which is also what we use in our sedimentation tank. It's steep enough that just about anything will slide down that steep of a slope. And then you might say, well, how did you decide how many hoppers to have? Or like why didn't I make those hoppers even taller? And if you think about why not make them taller, which I could easily do, like I had the space, in order to make those hoppers taller, I would just drop this, I would move the bottom of this system down further. So anybody have an idea? Why wouldn't I make the hoppers a whole lot taller? And so I could have done this with one hopper. I could have just had one big hopper, Why not? It would work.
Would it have to do with how the water flowed through? Would it like be too much of a head loss to go down and then back up?
So the water doesn't go where we want it to go. The water just kind of finds the straightest path to go through. So the water actually isn't going to go down into the hopper, or most of it is going to just like slide along the top. So that's not a problem, but good question. What else might be like a constraint that would say going with one deep hopper might not be the best solution? Okay, I think the last time we met, I suggested this idea of be an extremist. And it's like take things to the extreme in both directions and see what happens. So here I'm saying go to 1, which is as far as we can go. We can't really go to 0. That doesn't make much sense. We'll go to 1, and you could also go to infinity on the other end. And can you tell me what happens to the volume of concrete required to build the hoppers as you vary from an infinite number of hoppers down to 1 hopper? This is kind of a fun result. Can you see it? Can you draw the picture in your head? What happens if you have infinite number of hoppers? How much concrete do you use for just for the hoppers? Anyone?
Too much.
Wait, what does it look like? The hoppers are a nanometer tall, and they're along the, maybe I didn't actually hear what you said. In any case, the answer is not much. It goes to 0. The concrete that's in the mountain goes to 0 if you turn that mountain into an infinite number of mountains that are a nanometer tall. So I'm not sure if you believe me. Do you believe me? Are your thumbs up, or are you like, how about it in this case? If I have my 1 nanometer tall mountains, the area under the curve is at most, well, it's half a nanometer. I've got a half a nanometer average height of concrete. Okay, so it goes to 0. So infinite would be the way. Economics would tell you that if you're just trying to save concrete, you should go to an infinite number of hoppers. And economics also tells you that going to just 1 hopper is the worst solution, because that's when you have the most concrete. So that's one reason not to just use 1 hopper, is you have to put a lot more rubble and concrete in place to make that. Going to a small number of hoppers also means that you have to buy more pipes, because you need a little plug for every hopper. And of course, we come up with some unrealistic situations here, but you end up having too many pipes if you have too many hoppers. And then the other thing is, you would like if a plant operator can grab a hold of the top of this pipe, pull it out, let the thing flush, and then put the pipe back in again. That means that the pipe should be like human length. It shouldn't be really, really long, or it's going to be hard to like get it back into the hole again. So that's another constraint. And by the way, you might think here, okay, we're being super spendthrifts in that we're not putting valves on this. This is one case in the plant where, yeah, you could put valves on this, but it would be a disaster. Because what's being removed here? All this gritty stuff, including small pieces of gravel that get brought in from your water source. And if you had a valve in the bottom of these tanks that you would open up and then close down again, eventually you would get some piece of gravel caught in that valve, and you wouldn't be able to get it closed, and the operator would get frustrated and it would crank even harder, and you'd have that valve broken. So the cheap solution is actually the easiest one to maintain. Wow, I think I might have answered Michael's question. It is a case where like, should it have been, I guess I have 1, 2, 3, 4 hoppers there. Should it have been 3? Should it have been 5? Where you'd have to like really go into optimization of cost to figure out that one, which is kind of cool because now we could actually do that. Now with our system, we could make the change and see how much the cost changes to see which end up being the cheapest option. Of course, we're not taking into account labor when we do that, but we can at least get a sense. So that's one thing. Another constraint besides physics is economics, which I just mentioned about, like, you don't want to use more concrete than necessary. Another one is fabrication. Oh, economics. I think I pulled up the diameter of that overflow pipe, and the diameter of that overflow pipe is partly determined by economics as well, because a bigger one would work even better. So there's two constraints that fight. There's a hydraulic constraint that says it has to be a certain diameter in order to carry the water that might come into this entrance tank, meaning the plant flow rate, and dump it. If the two trash racks, or if the trash rack completely clogs, that's your worst case scenario, and that overflow better be able to dump all the water coming into the plant so that it's not just spilling out over the floor. So there's a hydraulic constraint, and then the hydraulic constraint says that anything bigger than, I'm guessing that's a 4-inch diameter pipe, anything bigger than 4 inches is great. And then your economics constraint comes in and says, okay, but I'm not going to put a 20-inch pipe there because that costs me a lot more money. So economics or resource efficiency is always there. And then for an example of fabrication, if you look at the top view at the top of the slide, it has to be human scaled. So this tank has to be wide enough so that a human can get in it to fabricate it. And that ends up being a really entertaining constraint, because if you have a channel that's only 15 centimeters deep, then a human doesn't have to get in it to fabricate it. And so a channel that's only 15 centimeters deep can be fabricated even if it's only like a little bit more than a hand wide. So a shallow channel can be fabricated when it's hand wide, but once you have to actually get your whole body in there, then it's the dimension of your hips and maybe a little bit about how much your elbows have to move around while you're fabricating that ends up setting how wide is reasonable before the masons that have to fabricate this start complaining about how this is impossible to build. And believe me, like those are issues that you absolutely have to think about when you're designing things. If you design something that can't be fabricated, you're going to be famous on the job site, and you don't you don't want to be famous on the job site in that way. Anybody want to ask a question about that? Follow up. And I'm curious, when you're browsing on Unshape, I don't know what you can see. I know what I can see, but I don't know what you can see. I know that almost all of our material is open source. Is there a way that you can actually easily find like all of our files? Anyone? Like, can you see entrance tank, flocculator, sed tank? Can you easily see that stuff somewhere? Haven't tried? Try it and let me know how that is. I'm hoping that you can easily find that. And if not, we'll figure out how to make it easier. Okay, the next thing I want to talk about is applications of flow control. When is flow control important? One example is if you're going to do point of use treatment. So if you're going to treat water in your own home, then you need to figure out some way to control the flow rate through your little treatment device. Otherwise, it's not going to work as well. Examples are clay pot filters, slow sand filters. Maybe you're trying to remove arsenic and fluoride. And I really should have had some images here, but apparently I was too lazy. When I was in Honduras in the 80s, I was trying desperately to make a slow sand filtration device that would work for my own home. And one of the critical pieces is figuring out how do you get flow control to work nicely. We need to add chemicals for a water treatment plant. So some aluminum or polyaluminum chloride as a coagulant. And we need to control the dose of those and make it easy for an operator to increase or decrease the dose. So that ends up being critical. Another one is chlorine for disinfection. Maybe you need to add sodium carbonate or hydrochloric acid. Sodium carbonate to control pH, hydrochloric acid to drop the pH a little bit to prevent calcium carbonate precipitation. One of the things that we've done in one of the plants in Honduras, and yes, you need to worry about whether you end up dropping the pH too much and you're causing solubility of lead in the distribution system. So if you have electricity, then this is what you do. So you use a metering pump. So here's a piston pump. Piston pumps are great and can be used to meter chemicals. The problem would be that the piston itself, that whole system needs to be compatible with the chemicals that you're using. And so this would not be the way you would want to meter chlorine. You can use a gear pump. Gear pumps are fascinating. Yeah, also lots of sliding surfaces and another issue of making sure that everything is chemical compatible. There's peristaltic pumps. This is the system that you would have in the AguaClara lab that you're building there at OSU. Peristaltic pumps, the easy way to think about it is if there was a garden hose laying out on the ground and you walked down the garden hose, putting one foot in front of the other, and as you're going, you're squishing the hose, you would push some water out the end of the hose. That's all a peristaltic pump does. And the cool thing about a peristaltic pump is that the only thing that touches the fluid is the hose. So the rollers that are smashing the tubing don't ever touch the chemicals that are inside the tubing. And so you can pump really nasty chemicals with a peristaltic pump. Same thing with a diaphragm pump. In some ways, it's very similar idea. You have some flexible membrane that you're pushing back and forth, and that's acting like a piston, but it's flexible and there are no sliding surfaces, but there's a surface that has to deform. So some cool ideas. Another completely different idea would be that you would have maybe a stupid pump, like a centrifugal pump or maybe a gravity powered system that's providing pressure and pushing water towards your water treatment plant. And you could control the flow of that water by having a flow sensor that's measuring head loss and using that to figure out what the flow rate is perhaps. And then you could have a computer that controls how far open the valve is to control the flow into the plant. That is a very, very common system used in water treatment plants for controlling main flows, main flow into the plant or controlling flow into the filters. And what I am learning about that system is that very, very frequently those systems have problems with cycling, where they have lousy control on the software side. And so it ends up cycling and you end up not getting the nice consistent flow of water through your plant that you would like. But it's an option. And so my conclusion here is one option is to just raise the per capita income of everybody on the planet, make everybody have access to electricity and easy access to all these parts. And then all this stuff works great. And indeed, that's true. Like if you're in a community here in the US, they can afford to replace their pumps every few years and that whole system works. And I would argue that there's another approach. And the other approach is like going down a completely different path of this evolutionary chain that we're on, where we, instead of using pumps, we figure out a system that doesn't have any moving parts, but that still uses good physics to make it work well. I already talked about those observations. Well, I'm going to talk about those. So here's, and I know that some of you were in the presentation I gave when last fall, And I talked about this case of a plant where all the pumps were no longer working and the operators were bright, and they just used that garden hose and they put a kink in the end of that garden hose so that they could control how much flow was going through that garden hose. And that's how they set the chlorine dose for the plant. I think it's pretty cool. So I wonder, if we think about what was good and what was bad about that design. So on the good side, it's simple. All you have is a garden hose with a kink in it. So it's exceedingly simple. It's low cost. It's a part that they can buy at the local hardware store, and there are no moving parts. Like, that's actually like a super elegant design so far. What are the cons? Cons are that you're imagining there's this kink, and the way they were adjusting that kink, like how hard is the hose doubled over, and hence how big is the orifice that the coagulant is flowing through in the kinked part of the hose. They were wrapping string around the doubled part of the hose and adjusting how tightly they had that string to adjust how much flow they would get through the hose. So the con is that setting the dose is kind of a mess, right? You can unwrap your string and open up the kink a little bit and then rewrap it to hold it there. But adjusting the dose is not intuitive. You can't easily see what's going on. It's probably not even very repeatable. And then there's another problem. The flow rate is going to slowly decrease over time as the chemical level in that big black tank goes down. And that's because that chemical level ends up being the driving head that's pushing the chlorine through that kink. And so as there's less elevation in that storage tank, less chemical comes out. And then the last one is actually pretty important. And that is, this is based on a siphon. I have a question. How many of you have at one time in your life or another used a siphon at any scale to get a fluid out of a tank and into somewhere else? Who's used a siphon at least once in their life? Okay, so there's like 75% of you who have never used a siphon. I would recommend that the very first thing you do today is you go buy a packet of those straws that have the bendable end, and you make a siphon and empty your glass of water with it. If you've never done that, you have to do that at least once in your life. And I mean, you can do it over the sink so that it spills in the sink. And you can figure out, like, you can have the challenge of, can you figure out a way to start that siphon without sucking on the end of the straw to get it started? Which is a useful skill just in case you're ever in the situation where you need to siphon gasoline out of someone's tank. It's good if you know how to do that without sucking on it. Wow, I didn't really intend to, like, I don't know, help you into a life of crime. But learning how to siphon a fluid is a useful thing. So do that. And my point here is that starting a siphon with chlorine is hazardous, because the last thing you want is a mouthful of Clorox because you sucked a little bit too long. Yeah, and another example of dosing, and I think I'm showing these because when we began this journey of wanting to design water treatment plants, I recognized that figuring out this part of how do you dose the chemicals was like top priority, because if you don't have that working, none of the rest of the plant works. And so that became the very first task that we worked on starting in like 2004. We started hitting this question about how can you make a good system for dosing chemicals? And what's fascinating is, like, that was in 2004. Like, people have been doing water treatment for a very long time, and yet there there weren't great examples of how you dose chemicals if you don't have access to electricity into pumps. And here's another example. Here's a saltwater electrolytic chlorine, which I misspelled, generator. And so there it is. It was in a town in Nicaragua, in Concordia. And what's fascinating is I realized when I looked at this that it wasn't working. And I walked around to the back of it and I saw this. So on the back side of this was another chlorine feed system. That T is, the cap of that T is meant to be removable, although I tried and couldn't. And what you do is you drop a chlorine tablet. So it's like a hockey puck of chlorine that you would drop in that T, and you might drop several of them in there. And then some of the water is flowing past that T and dissolving that chlorine tablet over time. And if you get the flow rates right, because you don't send all the flow past the hockey puck, you only send some of the flow that's going into your storage tank past the hockey puck, you can kind of regulate the dose. I'm still waiting to see, someone must have done studies on these to figure out how good they are. This is an option. You can buy this in the US. They're being installed many places on the planet. I've always been skeptical about how good the chlorine dose is as a function of time, but maybe it's not bad because they're being used many places. But what's interesting here is I'm pretty sure that system wasn't being used either. So there was like plan A, not in use, the one that required electricity. Plan B, also, as far as I could tell, they weren't adding any chlorine. And this is a place where an AguaClara plant went in as plan C, I guess that would be, or Roman numeral 3. Okay, so we're going to talk about different ways to control flow, and we're going to start with this hole in a bucket idea. And this comes from Honduras, where they have chlorinators on storage tanks. So we're out in the mountains, and there's this distribution tank. You can see the pipe from the mountain spring or stream comes here, and it goes up and dumps into the top of the tank. And then there's this mystery little cube on top of the tank. And that mystery little cube is a place where there's some magic happening. So this is what's inside that magic tube, inside that magic cube. So there's the magic cube. It's a little tank where you would mix up a chlorine solution using calcium hypochlorite. And then there's a PVC pipe coming out the bottom, and there's a valve at the end here. And you can open or close that valve to set how fast the chlorine drips out of that tank and added to the raw water that's coming into the tank from the stream. Any questions about how that system is working? You got a tank of chlorine that's on top of the tank. That's going to be your storage tank for water. Water's coming into your storage tank, running by gravity day and night, and you're dripping chlorine in from this little storage tank. So what happens to the chlorine flow rate over time? So what happens over time? The chlorine level drops in that tank. And so the elevation difference that's pushing the chlorine through that valve is dropping. And you can think about that orifice equation again, where the flow rate goes with the square root of the height. Or said another way, the head loss through that valve is proportional to V squared. In either case, you see that as the height goes to 0, the flow goes to 0. And so as the chlorine solution is used, the dose of chlorine changes. And that's not at all what we wanted. We wanted a system that would give a constant chlorine dose all the time. And so this isn't working. But what's interesting is that, well, I'll come back to that in a second. This is why it doesn't work, because of the orifice equation that says that the flow is proportional to that delta H. So we're going to find out what does the flow actually do as a function of time? And the derivation for this is in the textbook. The derivation involves integration. It's not that complicated, but the result is what's really cool, and it's what I'll show here. This is a result of taking into account the orifice equation, or another head loss, like minor loss coefficient equation, and tracking volume in the tank as a function of time, and comparing or having an equation that relates the height of the chemical in the tank and the volume of chlorine in the tank. So this is the beautiful equation that we get, that the flow rate at any time divided by Q0, the initial flow rate, is equal to 1. And if we stopped right there, we'd be really happy, right? If Q over Q0 would equal 1, that would mean that the flow rate at Q is Q at any time. That would mean that the flow at any time is the same as, is equal to Q0. But there's this second term in the equation, 1/2 times T over T design times H tank over H0. And that's what's going to get us, because as T gets larger and larger, that second term gets bigger and bigger, and my Q decreases, gets smaller and smaller. And so what's getting us? Well, as T increases, T over T design is the time it would take to drain the tank if the flow was held constant. So you filled up this tank, you set an initial flow rate, and you said, okay, at that flow rate, this is going to last 4 days. So that's T design. And when you come along and you come back at T equals 4 days, and if H tank was equal to H0, you would find out that the flow was exactly half of what you had expected it to be. So some reflections on this. If we let the discharge to atmosphere be located at the elevation of the bottom of the tank, so if H0 is equal to H tank, then the flow rate goes to 0 exactly when T equals 2 times T design. So you can look at that. When T equals 2 T design, then this second term is equal to 1. And that means that Q goes to 0. So that's how long it takes for the tank to drain. It takes twice as long as what you had initially expected based on the initial flow rate. So this is a nice result. What's the average flow rate during this process if the tank is drained completely? So if it takes twice as long to drain as what you would have initially guessed, it's because the flow rate on average is half of what you had expected. So the average flow rate out of the system is half of the initial flow rate. So if you take a tank like your bathtub and you fill it up and then you drain it, if you would measure the initial flow rate out of the bathtub when the bathtub is full, and if you would use that to predict how long it would take for your bathtub to empty, you would come up with a time that is exactly 1/2 the time that it's going to actually take to empty the bathtub. Okay? Kind of a cool, simple result. The average flow rate is half of the initial. But now the question is, we're trying to get this to work and to be much better. How could you modify the design to make it so that the Q is more constant? So take a look at that equation, or maybe your intuition will kick in. What could you do to change something so that the flow rate Q is always equal to Q0, or close to being equal to Q0? What could you change in the design? How could you make Q be almost constant?
I got a hopeful solution, keeping the chlorine at the same level, refilling that.
Okay, so you could have an operator come by and regularly fill the tank. Yes? Okay, that's one great solution. The operator doesn't love you, but it would work. Okay. What else could you do? Someone's got an idea. Let's see. Michael, what you did is you basically made sure that T was small compared with T design. You came back and you just kept on filling it frequently. So there's another term there. What could you, someone else, what could you do with the other term, with the H's? What could you do with those to make this so that it would almost give you a constant flow? Should I call in someone?
I can always go again, take a shot at it.
Oh, Michael, thank you.
If H of the tank was 2 times HO, would that result in same flow?
Okay, so if H tank was double H0, that would, hang on a second. If H tank is bigger than H0, that makes that whole second term get bigger.
Wait, so it'd be the opposite, I think. I think
We want to make that whole second term be as small as possible, which means that we want the terms on the bottom of the fractions to be as big as possible, or the terms on the top of the fractions to be as small as possible. So we could make T design be huge. That works, which is basically building a really, really big tank and only using the top part of it, which is similar to what Michael was doing earlier. Or we can make H0 be really, really big, what is it? Let's set H0 to be 50 meters and H tank to be 1 meter. Now, do you have a picture of this in your head? What does this look like? This is why we need Onshape. We need to just like draw this right away. What does it look like if H0 is 50 and H tank is 1? What do you have? You've got a tank on stilts. It's 50 meters up in the air and it works great. But just like the other solution that Michael suggested, the operator doesn't like it. Do you know why? The operator does not like climbing 50 meters up in the air and mixing up a chlorine solution, right? So it works, the equations work, but it is not an elegant solution. And indeed, this is just like, we've demonstrated that there's a problem here. You can kind of solve it, but in order to solve it well, you end up with ridiculous solutions. And so this is not a great option. And this is what I'm feeling right now. I'm feeling like I've been talking for an hour, and that's about as long as you max out at anyway. And I'm wondering how many of you have started the assignment for next, that's half due on Tuesday. How many of you have started? Okay, so this is what I want to do. Let's go into GatherTown, and each of your teams meet on around one of the tables and stay there for the rest of the session and start working on going through the entrance tank problem. And I will rove around and be there to answer questions. So let's reconvene in Gathertown. See you there. Any questions before we go? All good? Gathertown, bye.